first thing is about all the chemical species. We can see a signal in a mass spectrometer if they are charged species, and in most of the instruments, yeah, the kind of species we can see signal they are cations. Okay, and the simplest cation is a molecular ion. So it's for example, this guy is a neutral molecule. After losing one electron, it becomes a molecular ion. A molecular ion typically, molecular ion typically is a cationic free radical. And in many cases, a molecular ion could undergo fragmentation, give you smaller ions. In the mass spectrometry, they are called daughter ions. Okay, it's actually a sexist term. Just kidding. Why they don't call sun ions? But anyway, just the smaller ions. Okay, so one of justification for those smaller ions to form is because if a particular smaller ion has unusually high stability, means the particular cation has some the enhanced stability, that kind of particular ion has a greater chance to form. Like in this particular example, it's called propylbenzene. And we know the molecular weight of propylbenzene is 120. Look at those, we forget about those numbers of decimal point, just a whole number, 120. So that's how we see this 120 peak, that's molecular ion peak. But the strongest peak, called phase peak, in a mass spectrum, is actually has a mass charge ratio of 91. So why that peak is so strong is because the molecular ion can undergo fragmentation, lose an ethyl radical, and give you a benzylic carbocation. And I hope you guys recall from Organic 1, Chapter 12. Benzylic carbocation is the most stable type of carbocation we have seen in probably Organic 1. Is because of in a benzylic carbocation, the positive charge can delocalize over 4 carbon atoms. Here, benzylic carbon, and this carbon, and this carbon, and this carbon. So that's why benzylic carbocation, they are, one, very stable kind of carbocation. And that's why the molecular ion is willing to lose the ethyl radical and give you a stable benzylic carbocation. That's just, one of the reasons. And late in the, many later chapters, we will see other situations where the more stable carbocation will, kind of those carbocations with enhanced stability will form and they will show their signature in the mass spectrum. And then if you recall what we have discussed so far, the most important information generally we get from a mass spectrum is molecular weight of your compound. Okay? And the molecular weight actually can give us, the quite a bit of information. First thing is, once you know the molecular weight, you actually have a pretty good idea about, what the molecular structure might be. Okay? And for instance, there's one rule called nitrogen rule. Okay? So if you are dealing with organic compounds, and a typical organic compound, we know it must have carbon, must have hydrogen, not must, but usually must have carbon, usually has hydrogen, often has oxygen. Okay, so must have carbon, usually has hydrogen, often has oxygen, and it might have nitrogen as well. Okay, when you deal with this kind of organic compounds, and if the compound's molecular weight is order number, okay, then it must have order number of nitrogen atoms. If the molecular weight is even number, it must have even number of nitrogen atoms. So, for instance, if the molecular weight of a compound is say 138, immediately you say must have 0 nitrogen, 2 nitrogen, or 4 nitrogen. It cannot have 1 nitrogen, 3 nitrogen, or 5 nitrogen. Okay? So this is a nitrogen rule. Okay? So similarly, like here, the molecular weight of 93 means you must have either 1 nitrogen, 3 nitrogen, 5 nitrogen, or 7 nitrogen. Okay? So obviously here you have 1 nitrogen. So this is one, one kind of hint you can get from molecular weight alone, the nitrogen rule. And in many modern mass spectrometers, you actually can directly get, high resolution, mass number, very high resolution molecular weight of your unknown. And when we talk about molecular weight, usually we talking about, at least in the framework of mass spectrometry, when we talk about molecular weight, we're talking about whole number molecular weight. So that is not, the whole number molecular weight does not have very high resolution. For instance, these two compounds, left side is octane, right side is cyclopropyl acetate. You don't need to worry about the name, but what you could see is they have totally different molecular structure, and obviously also different molecular formula. But both of these two compounds has a molecular weight of 100 grams per mole. On the other hand, if you put these two compounds into a high resolution mass spectrometer, okay, you actually the high resolution mass spectrometer can actually get the molecular weight at extremely high precision. So and if you look at the molecular weight of the two compounds, at a precision of 4 decimal points of 4 digits of the decimal point, you will see that these two compounds obviously have different molecular weight, and that kind of high resolution molecular weight, in mass spectrometry has different term called exact mass. Okay, just to signify the precision of the molecular weight called exact mass. So for a good high resolution mass spectrometer, you can basically have confidence to the fourth digit of decimal point. So basically, you can say, probably this. You all know from general chemistry, whatever number you get from the experiment, there's always the issue of significant figure. Okay, so the significant the exact mass is given as how many significant figures here? 7 significant figures. Okay, that means that the very last digit, this digit, you might have a certain error, okay, maybe plus minus 2, plus minus 3, depending on instrument. But at least this digit is somewhat called estimated. Okay, but this one absolutely reliable. Okay, so with this kind of data, you can clearly see those two guys are different. Okay, you can resolve these two compounds with different molecular formulas. So if you have a high resolution mass spectrometer, those high resolution mass spectrometer, those modern ones always are equipped with the software. So once the spectrometer picks up exact mass, immediately can give you a few choices of the molecular formula. So usually the choices of molecular formula is very small, like maybe like 3 4 at most. Okay, so the based on if you are doing the study on a compound, usually you already have a hint from other analysis. You will know pretty sure only one of those 3 or 4 options is the right molecular formula. So basically, if given the high resolution, if you have a high resolution mass spectrometer, you can actually direct get molecular formula. So that's basically the major application of mass spectrometer. Yes, mass spectrometry has a much wider application than just getting the molecular formula. But for most of chemists, I'm not talking about most of chemists who use mass spectrometry, with very few mass specialists, okay, they probably can apply the mass spectrometry to much deeper aspects of the mass spectrometry. But for most of chemists, getting molecular formula is most important aspect. Okay, and that's all also I'm asking you guys to do basically. Okay, so if you have a mass spectrometry data, usually it will give you the molecular formula. Okay, and but if you really think about tests, you don't need to worry about how you get a molecular formula from mass spectrometry. Okay, basically, what you will be facing a question is, okay, from mass measurement, you know the molecular formula. This compound is like XYZ. Okay, CX, HY, OZ, NA, whatever. Basically how many number of carbon, hydrogen, oxygen, nitrogen atom in the molecule. Okay, then you will be asked something else. What's something else? First thing is about the index of hydrogen efficiency. Okay, once you have the molecular formula, let's say look at simplest examples. Only look at carbon and hydrogen. Okay? So you know that from the what we learned in organic 1. So I hope you know this, but if you don't know, just just refresh your memory about alkanes. What's the general formula of alkanes? Is CnH2n plus 2. Okay, alkenes they are CnH2n. Okay, and cycloalkane also has a general molecular formula CnH2n. So cycloalkane. Okay. So what you see is, the alkene, we have a pi bond. Okay. So we lose 2 hydrogen compared to alkane. Okay. So this is alkene. This is alkene. So the alkene, we have 1 pi bond. So we lose 2 hydrogen atoms compared to alkane. And the cycloalkane, we don't have pi bond, but we do have a ring, so we also lose 2 hydrogen compared to the regular alkane. Okay? And if you look at the cycloalkane, just using this example, cyclohexene, if you count the number of carbon and hydrogen, you will see cyclohexene has a molecular formula of C6H10. Okay, we can do a bit of counting. Here you have the 2 hydrogen on each carbon, 8 of them, and here is 1, here is another 1. Okay, so basically that's a cyclohexene. In cyclohexene, it has 1 ring and 1 double bond, right? And 1 pi bond. Can say that way. Okay, so see the 1 pi bond makes the molecular formula lose 2 hydrogen compared to the alkene with the same number of carbons. And the 1 pi bond also makes the molecular formula lose 2 hydrogen compared to the alkene with same number of carbons. So cycloalkane has both, so lose totally 4 hydrogen. Okay, compared to the alkane with same number of carbons. So this kind of, the number of, the pi bond makes the molecule losing hydrogen compared to the alkane with same number of carbon, and the ring also has the same effect. The combination of these two effects can be described by a term called index of hydrogen deficiency. So they basically just they tell you the total number of pi bonds and the rings in the hydrocarbon. So how do we calculate index of hydrogen deficiency? So the first, we will get the molecular formula of the hydrocarbon we're going to dealing with. Okay, CnHX, that's the molecular formula. Then you will write out the molecular formula of the alkane with same number of carbons. Okay, that's always CnH2n plus 2. If you forgot, just refresh it. Okay, then you just minus these two guys. The carbon number is same, so they get cancelled. So only difference is the hydrogen number difference. Then because of each pi bond gonna cause the molecule lose 2 hydrogen, and each ring also gonna cause the molecule to lose 2 hydrogen. So if we want to know the total number of pi bonds under the rings, we just take the difference divided by 2. That's the index of hydrogen deficiency. Okay. And if we are dealing with more complicated molecules, if it's not a purely hydrocarbon, that means we could have heteroatoms. If we have a halogen, we just consider, halogen replace 1 hydrogen. So we add 1 for each halogen. You count the number of, hydrogen. And for nitrogen, if each nitrogen we minus 1 hydrogen. And for oxygen, there's no impact. So that's how do we calculate index of hydrogen deficiency. Okay? So let's look at a few examples. Okay? So let's just calculate index of hydrogen deficiency of a pure hydrocarbon, say C7H14. C7H14. So the first thing we should write out the molecular formula of the carbon has same number of molecular formula of the alkane with same number of carbon. So that is C7H16. Okay. So minus the structure we are dealing with C7H14. Okay. And then we divide it by 2. So that's equal to, so here cancels. So 16 minus 14 is 2 hydrogen. 2 divided by 2 is 1. Okay. So that means if you have a molecular formula of C7H14, either it has a 1 pi bond, or 1 ring. So that's what you can learn from the index of hydrogen deficiency. And in the practice exam, there was one question asked you to draw the molecule, the structure of the molecule with the molecular formula, I believe C14H22, with the longest lambda maxima. Okay, so for that molecule, C14H22. Okay. From the molecular formula, you can calculate index of hydrogen deficiency. Okay? So in this case, you first write out the molecular formula of alkane with 14 carbons. So that is C14H 2 times 14 plus 2. Okay? So this is equal to C14H30. Okay? So then the index of hydrogen deficiency of such a molecule is CS C14H30 minus C14H22 equal to 30 minus 22 is what? 8, right? 8 divided by 2 equal to 4. Okay? So this molecule can have up to 4 pi bonds. Okay, So that's what you calculate from the index of hydrogen deficiency. Okay, up to, I'm saying up to. You could have 4 pi bonds, 0 rings, 3 pi bonds, 1 ring, or 2 pi bonds, 2 rings, or you have 3 rings, 1 pi bond, or 0 pi bonds, 4 rings. Like, all these combinations are possible. C712, C7H12, okay? Do the same thing. You find that the alkane with 7 carbons, molecular formula C7H16. Then minus C7H12, in the parentheses is like 4. 4 divided by 2 is 2. So that means this molecule could have 2 pi bonds, 2 rings, or 1 pi bond plus 1 ring. And in the case of 2 pi bonds, could be, let's just make clear. Why I'm saying 2 pi bonds? 2 pi bonds could be 1 triple bond, okay, or 2 double bonds. Just keep in mind each triple bond has 1 sigma bond plus 2 pi bond. If you forgot, please do check organic 1 chapter 2, okay, and the chapter 9. So each triple bond has 2 pi bonds. Okay? So if a double bond is a 1 pi bond, each double bond has 1 pi bond. So the index of hydrogen deficiency could be 2 rings, 1 triple bond, 2 double bonds, or 1 double bond plus 1 ring. So the 1 triple bond and the 2 double bonds in both cases reflect, both cases you have 2 pi bonds in the system. If you have oxygen in the molecular system, you don't do anything. Just you can assume as if oxygen does not exist. Okay. So if we have the molecular formula C7H16, you just find the alkane with 7 carbons. We know that's C7H16. So you can just ignore the oxygen. Obviously, your compound has same number of hydrogens as the alkane. So the index of hydrogen deficiency is 0 for this compound. That means this compound has neither ring nor the pi bond. Okay. Under the another example of oxygen atom. Look at this guy. If you count, number of hydrogens, you have 3 hydrogen here, 4, 5, 6, 7, 8. Totally 8 hydrogen. Okay. So the molecular formula is C5H8O2. Okay. So because it only has oxygen, so we just when we calculate index of hydrogen deficiency, just directly ignore the oxygen. So we just find the hydrocarbon, the alkane, with the same number of carbons, 5 carbons. So the alkane C5H12. Then do the subtraction in the parentheses under the H12 minus H8 is 4. 4 divided by 2 is 2. So basically, this molecule has an index of hydrogen deficiency of 2. That means this molecule could have 2 pi bonds, 2 rings, or 1 pi bond plus 1 ring. And in the structure shown here, obviously, what kind of situation we have? We have 1 ring here and 1 pi bond here. And if you have a halogen, you can treat a halogen as if it were hydrogen. So the example give here, C3H5Cl. So we just, when we calculate index of hydrogen deficiency, just replace the Cl with the hydrogen. So we treat as if as if it were C3H6. So then, the do the calculation. So the obviously for 3 carbons, okay, the alkane is C3H8, okay, then minus C3H6, and divided by 2, okay. That index hydrogen deficiency is 1. So that means the 1 pi bond or 1 ring. Here is 1 pi bond. And if you have a nitrogen, you just have to subtract, the 1 hydrogen for each nitrogen. So here this guy molecular formula C6H11N. So when we calculate the index of hydrogen deficiency, we will subtract, the subtract number of hydrogen for each nitrogen we have in the molecule. So if we want to calculate index of hydrogen deficiency, it will be C6H10. Treat this as C6H10. Okay? And then obviously we know first thing we need to find the number of alkane. We need to write the molecular formula of the alkane has the same number of carbon atom as this molecule. So it's C6 and H14 minus C6H10 and divided by 2. So that is half times 4, that's equal to 2. So that means you could have 1 pi bond plus 1 ring, 2 pi bond or 2 rings. And the example shown here, we have 1 pi bond and 1 ring. So now the index of hydrogen deficiency will tell us the number of pi bonds and rings in a molecule. But is there any way for us to know, how many rings we have in a molecule, or how many pi bonds we have in a molecule? There's no direct method. We can know how many rings in a molecule, but there's a fairly reliable method for us to know how many pi bonds in a molecule. So this method is a reaction we learned in Organic 1, chapter 8, reactions of alkenes. I hope you recall that, the CC double bond in the alkene could react with the hydrogen gas, in the presence of catalyst. That catalyst often is platinum, okay? But they also could be palladium, nickel, rhodium, a few different catalysts. And that's called catalytic hydrogenation. Okay? So in a catalytic hydrogenation reaction, each pi bond can react with 1 H2 molecule. So 1 pi bond reacts with 1 H2 molecule. And the ring does not react with H2 molecule. So if you can look at, if you have if you let let's say you get an unknown compound, you're asked to do analysis, unknown compound asked to do the analysis. So you already get the index of hydrogen deficiency, okay? Now you want to determine how many pi bonds they have. Just you measure how much, the molecular formula already, okay? So you know the molar mass. You just put, say, 1 mole, assume, okay, 1 mole of such a compound, and then put it into a catalytic hydrogenation reaction, and give a sufficient amount of hydrogen, okay, sufficient amount of hydrogen. Then you can calculate for each mole of your compound, how much hydrogen, how many moles of hydrogen molecule you can react with, how many moles, okay? So that will tell you the number of pi bonds in the molecule. So for instance, let's say I just randomly make up a molecule. Say C8H8O2, okay? this molecule. Okay, so the this molecule, if you let it subject to a complete catalytic hydrogenation reaction, complete catalytic hydrogenation. Okay, I would say complete means you have a sufficient amount of hydrogen supplied. Complete catalytic hydrogenation. Okay, and every mole, each mole of the compound can react with say 2 moles, okay, hydrogen. Okay. The question is how many pi bonds in the molecule? How many pi bonds? How many rings? Okay. First we need to calculate the index of hydrogen deficiency. Okay. So because here we have oxygen, okay, so does not impact. Just you can assume as if oxygens do not exist. Okay, so you just write out the molecular formula of alkane with the same number of carbon. That be C8H what? How much here? 2 times 8 plus 2. So it's C8H18. Okay. So then you do the index of hydrogen deficiency. C8H18 minus C8H8 divided by 2, that is equal to 5. Okay. So now the index of hydrogen deficiency 5 means the total number of pi bonds plus total number of rings equal to 5. Okay, that's how what index of hydrogen deficiency tells you. Okay. Now, because each mole of compound can react with 2 moles of hydrogen. Okay, so that means how many pi bonds? 2 pi bonds. Okay. Therefore, 3 rings because of number of pi bonds plus number of rings equal to index of hydrogen deficiency. Okay. So here concludes the chapter 14. So we covered everything.